Free fall. If you roll two balls of different masses down identical inclined planes, which one will reach the bottom first? Galileo demonstrated that they reach the bottom at the same time. This may not seem intuitive. You may have guessed that the more massive one would reach the bottom first. But due to the Earth's gravity, all bodies at the same location above the Earth fall vertically with the same acceleration. When this gravitational acceleration is the only acceleration that a body is undergoing, we say that the body is in free fall. In most real situations on Earth, when a body is falling due to gravity, it also feels some air resistance which slows its falling a bit. In physics problems involving freely falling bodies on Earth, we will ignore air resistance. Earth's gravitational force accelerates objects toward the center of the Earth. An object closer to the center of the Earth feels a greater acceleration than does an object that is much farther from the Earth's center. Near the surface of the Earth, the magnitude of acceleration due to gravity, which we will call g, has been measured at 9.8 meters per second squared. This acceleration is approximately constant when the distance an object falls is much smaller than the radius of the Earth. Most of our introductory physics problems involving free fall are near the surface of the Earth, so we can use this constant 9.8 meters per second squared as our gravitational acceleration. Since this acceleration value will be constant in our free fall problems, we can use the kinematic equations to solve these problems. Let's look at an example problem. To help myself decide between my two favorite ice cream flavors, I toss a coin in the air. I toss the coin up with an initial speed of 4 meters per second. Ignoring air resistance, how high should the coin go above the point I released it? Before we draw our picture, let's look for some key phrases in the problem. First, ignoring air resistance. If we ignore air resistance, we can treat the coin as a freely falling body, which means constant acceleration, which means we can use the kinematic equations. The second phrase that gives us a clue is how high should the coin go. This means that we're looking for the maximum height of the coin, and at the maximum height, the coin should have a zero upward velocity. Now let's draw our picture. First we have the coin moving upward with a velocity of v1. Then we have the coin at maximum height, delta d, with a velocity of v2 equals 0. And we will choose up to be the positive direction. Now, what values are we given? Our initial velocity, v1, is 4 meters per second, and our final velocity at maximum height is 0 meters per second. Also, since it's a freely falling body, the coin has an acceleration of minus 9.8 meters per second squared. The acceleration has a negative value since the acceleration vector is pointed downward toward the Earth, and up is our positive direction. Next, what are we looking for? The maximum height of the coin, which is its displacement. Now we need an equation. Looking at our table of kinematic equations, we find one that contains v1, v2, a, and delta d. Since we're looking for displacement, we go through the steps to solve this equation for delta d, our displacement. Then we plug in our values for v1, v2, and a. Finally, we use our calculator to solve, getting a displacement of 0.816 meters. This is the maximum height the coin reached after I tossed it upward. It's important to get the signs right on our values. Even though our acceleration had a negative value, the negative sign was canceled out by the negative in the numerator, giving us a positive upward displacement. It's a good idea to always check your answer to make sure it makes good physical sense.